Okay. All right. Okay. Um. So I'm thinking that one of the factors has to do with how much water you have.
Yeah, I think I put amount of water, but I didn't know how to explain.
So since I'm thinking it's because the different structures have varied amounts of water in their whatever their structure.
Hmm.
The more water you have, the more dispersed it could be in the crystal structure. So that means certain places may have more, and the other places might have less, changing what it technically is classified as.
Okay.
That's what I was thinking.
All right. I've also put heat for the second, or like sunlight. I put sunlight, but I'm thinking it's just heat.
Or heat,
Maybe.
because you could boil off the water or get rid of it or something like that. Maybe along those lines.
Okay.
Again, I'm not exactly sure. I don't remember
Yeah.
this question a long time ago, but those would be my guesses.
All right. But you like heat and the amount of water are the two, or could be two of the factors.
Yeah, heat
Okay.
heat for maybe you boil off some of the water or something,
Mhm.
and then the amount of water because it depends how much or like how dispersed it is.
Okay. And it's the crystals that are dispersed, like the.
The water dispersed inside of the crystals, right?
Okay.
While we're on the lab, can you scroll up
Yes.
just a little bit? I haven't looked at it in a long time, so I don't remember like exactly what it said. So I did my graph and I got my equation for my line, and then it asks us to calculate the concentration of our unknown. How do we use the equation of the line to calculate the concentration of the unknown?
So you. Oh, am I echoing? Um. So you have a graph of all your absorbances and concentrations, and then you should have an absorbance for your unknown, right?
Yes.
And so you can get your concentration from your trend line, right? Is that how you did it, Abby?
I think so.
Okay.
Let me look at it. Hang on, I gotta grab my lab notebook. I thought I wrote it.
No problem. No rush. I'm gonna stop.
This is for the concentration of the unknown.
Yeah.
Um, I plugged in, yeah, I plugged in my absorbance that I got for the unknown into the for y in the slope equation,
Mm-hmm.
and then you just solve for x after that, and that gives you your concentration.
Okay.
Makes sense.
Yeah. And then I don't remember what the question was before that, like right before the last question that you guys were going over when I joined, but like the next one, I don't remember what it asked. Let me see. I can't canvas up. Let me see. Oh yeah, no, that's fine. Okay, yeah, that's just using the number we get from the other one to solve for mass. So I know how to do that one. Great.
Janaya, what's your last name?
What'd you say?
What's your last name, Janaya?
Jania, but Williams.
Yeah. Okay, Williams. Okay, convenient. Both of your last names are Williams.
hmm
Okay. Sorry, I have to type in all your names. Which means I'll actually learn names better, faster. Anything else?
That's all for me on the lab.
Yeah, same.
Okay. Jania, did you have questions on the videos maybe? Or
I honestly haven't watched them yet. Not gonna lie to you.
Yeah, I haven't either.
Yeah.
we can here. We'll just work through some problems. Maybe hopefully this will work.
All right.
Okay. So I have this. So basically we're just calculating the pHs of weak and strong, or just weak bases, weak acids, strong acids, or just weak acids, weak bases mostly, because we've already done strong ones.
hmm
So let's see, I'm gonna do this. So we'll do this problem. Can't see it yet. There we go. Can you tell this is my first time? Okay. Can you see that?
hmm
Question? So that's what we'll do.
Okay.
So write it down, take a picture of it, whatever you want, and then I'll switch over to my whiteboard and we'll do it together.
I've got a picture of it.
Cool.
Same.
Awesome. All right. I'm done with that. Okay. You all can see this?
Yes.
Ooh, what I didn't do. All right. So we're doing benzoic acid. We got the Ka of it, so we know that Ka. Also, let me know if you can't see this. 6.5 times 10 to -5. Right?
Mm-hmm.
And I have my initial concentration. I don't care what it is. I'm just going to call it HA. 0.10 molar. Right now, we want pH. Okay?
Mm-hmm.
Do you remember doing this? I know it was a long time ago.
Yeah, it's a ice table with water being the base, right?
Yes. Okay. Right. Yeah, marker. So you're right, I have HA plus H2O comes to what are my products here?
Just A,
Yeah,
A minus, and then plus H3O
H2O.
plus.
Stable.
So acid is the other reactant, because, or not acid, water is the other reactant because it's the aqueous solution.
Yes.
Okay.
Yes, exactly. All right, got my ice table. So what goes here?
HA or the 0.1.
0.1.
Mm-hmm.
Go here.
The reactants, right? Because you don't write H2O within the ice table, right?
I don't care about this one. Good.
Right. Okay, yeah.
What goes there?
0
Good.
and 0.
Excuse me. Good. Now what are changes?
It's gonna be minus X for HA, and then plus X.
Okay. 0.10 minus X. X. Good so far?
Mm-hmm.
Yeah.
Okay, now what?
Put it into the equation for solving for Ka.
Oh yeah, okay. Yeah. So yeah, the Ka, so Ka is what? My 0.10 minus x over x squared, right?
Mm-hmm.
That's 6.5 times 10 to the negative 2. Are you guys comfortable solving that, or should we talk about it?
Comfortable solving it. Is the x is too small approximation, is that in chapter 16?
Yeah.
Okay.
Oh, this is the negative 5.
And so you solve for x, and then once you get that value, it's that value over the initial concentration?
If I assume x is small,
Mm-hmm. That for x is too small.
yeah. So if I assume x
Okay.
is small, I would get rid of this.
Mm-hmm.
Assume x is small. X is small. So I get rid of this one. Right. Delete that. Solve for x. So if I do this, what is x is going to be?
0.00255?
0.002.
Mm-hmm.
So if you assume x is small, the you still have to solve like x squared. You're still solving for that.
Yeah. You keep x squared.
Uh-huh.
Get rid of x if it's like minus or plus somewhere.
Okay.
So here I have minus x. If I had a plus x right there, I would get rid of it still.
Okay.
Mm-hmm.
Keep this x because
Keep
if
x squared.
you delete it, then you can't solve for anything, right?
Right. That's why I was okay. Got it.
Cool. 0.0255. Okay. All right. And then yeah, I take this number and divide
Mm-hmm.
that one.
Okay, right, and then multiply by 100 to get the percentage.
0.00255 over 0.10 times 100 is 2.5.
Mm-hmm.
So we're good.
If
Okay.
it's less than 5%, and you're good.
Yeah, it needs to be. That is definitely less than 5%.
Okay.
Okay. And so since this is a acid, we can just plug it into negative log the value of our x.
Correct. So just take negative log, so pH equals negative log, what's that log? 0.00255. So pH is what? We got 2.59%.
Mm-hmm. That's what I got.
Yep.
Awesome. Make sense?
Yeah.
Cool. Let's see.
So when you have a base, it'll work the same way, except you'll do negative log, you'll get that answer, and then do 14 minus that answer.
Exactly. So,
Okay. What about when, well, never mind. Because if water is your base, if water is your acid, okay, then it works the same, right?
well, if it works the same, so if I had this, but I was doing a base instead. Excuse me. So now I have a base up here.
Mm-hmm.
And then my product, the base, so bases do what with respect to our proton?
The bases gain a
Yeah, they gain an A.
proton. Should be like B plus.
Yeah, BH.
Yeah. Okay. OH.
What's going to be the other product?
OH negative.
OH minus.
Oh my gosh. Okay.
So assuming let's change the problem a little bit. It's KB, B, right? So right now we're in the same problem with respect to the base. So this didn't change, do the same thing. So now when we get here,
Mm-hmm.
what happens?
You would do well when you do negative log the x value. That's the POH.
POH, pH, like you said, 14 minus that.
Mm-hmm.
pH is 11.41, something like that.
So even when water is the acid, it doesn't exist in the ice table.
Yeah, the reason that we're ignoring it is because it's the liquid, right?
Mm-hmm.
Right.
Okay.
Yeah, and you remember what liquids are in our K expression.
Yeah, they have value of 1. Okay. Got it.
We're good?
Mm-hmm.
Yep.
Okay. Let's see. Here, why don't you do another, we'll do a base one. I'll give you a base one to do. It'll be a little different. Sure. Can you see that one?
Mm-hmm.
Yes.
Why don't you try to do that one?
Okay, it's not really a stupid question, but since it's it's a base because it's KB.
Yeah, correct. It's not a stupid question, it's a good one.
Then you assume that it's water because it's just a solution.
Yeah,
Okay.
correct.
I'm kind of stuck.
Oh yeah. So you have your, let me stop this. Okay, so you have your equation, you have your NH3 plus H2O goes to NH4 plus OH minus. Something like that?
Yes.
Okay. Do your ice table right. Ignore water. This was 0.18.
Mm-hmm.
Cool. 0, minus x plus x plus x 0.1 minus x. I'm assuming you weren't stuck there. Oh, Abby left.
I got all the way through it and I got 11.13.
Yeah, that's what I got. Okay.
Okay, good.
Hold on. Abby left. Oh no.
My Wi-Fi just cut out. Sorry.
Oh no, you're good. Okay. Were you stuck anywhere here?
No, I'm down to assuming X is small, I think.
Okay, so you got, I'm gonna mark there. So then doing your Ka or Kb expression. So you had the 1.8 times 10 to the negative fifth equals x squared over 0.10 minus x, right?
Mm-hmm.
So you're going to assume x is small, so you get rid of this guy.
Mm-hmm.
You multiplied by your 0.1 and then took the square root.
Yes.
Right, so you did x equals the square root of 0.10 times 1.8 times 10 to the fifth.
Yeah.
So you got x is
They're at 0.00134.
0.00134. Okay, now you have to check. Is that what you have to do?
What'd you say? Sorry.
Did you get stuck having to check it?
Yeah, this is where. Yeah, that's where I stopped at.
So to check, you take your x and you divide it by your initial amount.
Okay.
Right, so I do my 0.00134 over 0.1 times 100. What's that? That's like, is it 1.34%?
Mm-hmm.
So 1.34, right? It's less than 5, so that's good.
Okay.
Okay, so we checked it, so that's good. So that means we can just use this.
Mm-hmm.
So then what are you going to do with that?
You just plug it back up in the x. In the
Yeah.
ice table.
Yeah. And then, because I asked you for the pH, didn't I?
Yeah.
Mm-hmm.
Okay, so now what? How do I get the pH from here?
The negative log.
Okay, yeah, do the negative log of this. What's that going to give me?
.87.
2.87, and that is what?
That's your POH.
Yeah, pOH, good. So to get pH,
Is it 14 minus 2.87?
correct. What's that, 11, like 0.13?
Okay.
Right?
Mm-hmm.
Yep.
Cool. Okay, so that's that. So everyone comfortable with that. It's just basically, and then I could change what I ask. Like there are some book problems where they ask you, they give you a pH, and then they give you this initial amount, and they ask for Kb. So there's just different things you can do with that. We're not gonna worry about it right now. We'll just summarize the videos from it right now. So let's go to polyprotic acids now.
Okay. I was gonna ask, so I haven't watched the videos yet, but other than the beginning of chapter 16 that we were like already tested on, and these ice tables, is what you're about to do now, is that like the end of chapter 16 after that?
It's the close. So I think so. Polyprotic is nearing the end, but I think then there's a thing like you take salts, so things that look like, I'm not going to get into the details, but something like this, you can throw that in water and you get a pH.
Okay.
So I think that's at the end.
Okay. I was just trying to guesstimate like when the quiz would be, but okay.
I think next class, I have no idea actually. I feel like finishing chapter 16 in the next class, so the class after that one would
Yeah.
possible quiz.
Okay.
All right. Okay. So let me think. We'll walk through a problem together. Let's do that.
Okay.
Not sure yet. But you guys are hearing and seeing everything all right? There's nothing.
Mm-hmm.
Yeah.
Okay, good. I tried it earlier with my friends, but you know, things are different, and this is real time, so I'm panicking. Here. Okay. Okay. All right. So let's go over here now. Okay. So this is a question we'll talk about. Okay.
Yeah, I got a picture of it. What did you say this section was called again?
Polyprotic acids. So we're looking at acids with more than one H on them.
Okay.
Yeah.
Okay. Got a picture? Got your pictures?
Mm-hmm.
Yeah.
Cool. Stop. All right. So we're looking for the pH, right? But the thing we're looking at is H2C2O4. Or meant for, but there are two H's on here.
Mm-hmm.
There are going to be two equations. One where this first H pops off. So I'll write it bigger. So my first equation is going to be H2C2 plus H2O goes to HC2O4 plus H3 plus. Can you see that? Can you make it bigger?
Mm-hmm.
I can see it.
Okay, good. All right, so this is our first step. So we'll treat this like a normal ice table problem. So I, C, E. Got our initial amount of 0 to 5. Or ignore this guy. 0, 0. Okay, same thing. Plus x, you know, solve for. You do that again. 0, 5, find x, x. Easy, right? And then in the problem statement, I gave you two KAs, right?
Mm-hmm.
Okay. So KA1 is like it sounds, the KA for this first hydrogen to pop off. So that's for this first equation. So we get, so for this one, we do KA1, which equals 6.5 times 10 to the negative 2, which equals 0.25 minus x over x squared.
Mm-hmm.
Okay.
Now, do you still assume that X is small?
We could. I'm going to show you. So he did this in the video. It's a little trick to know when you can do that. So
Mm-hmm.
this number, so this is 10 to the negative 2.
Mm-hmm.
Right. And our initial amount, if we were to write it in scientific notation, this would be 10 to the negative 1. Right.
Mm-hmm.
I wrote it in scientific 10 to the negative 1. To assume x is small, generally what I want is for this to be 3 times less than that.
Okay.
Okay. So since it isn't, you could do it. You could try it. I'm almost guaranteeing that it's not going to work.
Okay.
Mm-hmm.
Okay. So I guess we can do it for practice. Let's do it. Well, let's actually, we'll look at it and see what happens. I changed my mind. Okay, assume x is small, so we solve this, and we do, so get rid of this guy. So I get x is what? Zero 0.16 is 0. So 0.01625. Is that what you got? Oh, square root. Oops. 0.1275.
Yeah,
Yes.
that's what I got.
Okay, good. Quick math. You could maybe see that that is most definitely half, or at least more than half of that.
Mm-hmm.
Math. 0.1275, 0.25 times 100. Yeah, 0.51 basically, or 51%.
So we want our Ka to be 3 times smaller than our initial concentration.
Yeah, you want this magnitude 3 times the worth of magnitude. So if this was like times 10 to the -4,
Mm-hmm.
then that'd be good. Because that'd
Okay.
be 3 times less than that one. Okay. All right. So x is small is not a good assumption, right?
Right.
Mm-hmm.
Go back and we have to solve it the hard way.
Okay.
Are you guys comfortable doing that, or you want to see it?
Doing the quadratic equation?
Are you comfortable with solving this now for x, or do you want me to write it out?
Oh, you don't have to write it out.
Yeah, it's fine.
So I'm just going to write x is equal, and then you guys can tell me what you get. Did you guys get 0.099 and negative 0.164?
I'm typing it into my calculator now.
I'm almost there.
No rush.
Okay, I have a question when you're doing the quadratic equation.
What's up?
So when I've got x squared, I've got my equation set up with x squared on one side and the other, and like b and c on the other side.
Yeah.
How do you know which one to move to get like the correct signs in front of everything?
It doesn't matter. Whichever one you want. So as long as, so you can move, so you have something, I think it's like negative, you have x squared equals what, 6.5 times 10 to the -2 x.
Yeah.
there's a negative right there. Minus what is and then you have 0.01625 minus that equals x squared. It doesn't matter what side you move it on.
Okay.
So as long as you keep your signs right, so you don't flip a random sign, you'll get the same thing. You should get the same.
All right.
I got the same values for you as for x.
Awesome.
Yeah, I did too. After I did that.
Cool. All right, then which one do we use?
The positive one.
Good. Okay. Okay. So you would think, right, previously, when we're doing non-polyphonic acids, you would be like, oh, I'm done here. I just need to plug that in and get my pH right.
Mm-hmm.
But now we have another step because this guy can still lose an H. Right?
Okay.
See that? So now I have another step over here. Right here. Block this off. Boop. H, oh, there's a minus right there. HC2O4 minus plus H2O goes to what's my C2O4 2 minus plus H3O plus again. Okay.
Okay.
All right, this is basically the same thing, but now I'm treating this as my acid.
Okay.
Okay, doing the same thing, remove the proton. Now do it again. So I see, okay. Okay. So I don't know if you know, but what amount do you think I'm going to put right here?
Is that
Is
the
it like-
0.099?
Yeah, the 0.099, right.
Okay.
Right, because this step happened first, and then this
Mm-hmm.
one. So now, right there.
So that x value is like your new concentration.
It's like my new starting concentration, right? I'm pulling my concentration, since these are the same, right?
Mm-hmm.
Pulling this concentration into this equilibrium thing.
Okay.
That H3O plus, we're going to do the same thing. So a lot of people, okay, this is where mistakes are made. Because generally, we just put zeros there, right? So you would think, oh, I'm just putting zeros here. But you do put a zero right there. But here you put the 0.099, right? Because I'm pulling it down for my previous one.
Okay.
Oh, okay.
Okay, so the main thing to keep in mind is to pull down your common amounts. So we've got HC2O4 minus and H3O plus. I have them down here, so I'm going to pull those final concentrations down here.
And so these concentrations will always match. Like for your second ice table, your initial concentration for your reactant, and the other one will always be the same.
In this case, yes. If I start out with zero of those two, then yeah, they'll be.
Oh, okay.
But if I have like an initial of that or initial of that, then they won't be the same.
Okay.
If you have like a 2x on the first ice table,
Yeah, I was going to ask that
whatever
next.
2x is into the next ice table.
A 2x? Wait.
Like it's yeah, if, for the HC2O4 minus in the first ice table.
Yeah.
If the equilibrium concentration, or no, if the change was plus 2x or something,
Yeah.
and you solve for 2x, you would put that value in the, you wouldn't just put the x value, you put the 2x value.
Down here. Yeah, right, correct.
Okay.
Yeah, good question.
So like keep the same stoichiometric coefficients.
Keep the same. So put whatever number you get for this,
Mm-hmm.
that into here. That's what I'm saying.
Okay.
If 2x, then calculate 2x. So those two should match, is what I'm saying.
Okay.
All right, make sense?
Yes.
Mm-hmm.
Okay. Then our problem rolls along similarly, right? So I put minus x again, because I still have that 0 right here, so plus x. Okay, so I got 0.099 minus x, x 0.099 plus x.
Will the change line ever be different from the first ice table to the second ice table? Like if you did minus x in the first ice table, you have the same minus x in the second ice table?
I think so. In most cases it's going to be the same because you'll never be coming back.
Okay.
There'll be when you're polyprotic stuff, you'll be shifting in the same way.
Okay.
I say most of the time because I feel like there's one example out there that is the counterexample. So.
Okay.
All right. Okay, so now we already used Ka1, so Ka2 is for this one, right? The second being lost. So we got Ka2 is what?
6.1 times 10 to the negative fifth.
Okay, so that's going to equal my x times 0.099 minus or plus x over my 0.099 minus x. Can you see that? That was kind of small. Okay, do we want to try this small here?
Sure.
Yep.
So let's see, we got -5.
Yeah.
And then what would that be?
That's 10 to the second?
Yeah, -2, right?
And that's 3 times. Yeah.
Right, that's 3, so let's do it here.
Wait, can you say that again?
So I'm checking my magnitudes, order of magnitudes. This one is 10 to the -5. This one, if I wrote it in scientific notation, I would put 10 to the -2, right? Because
Right.
2 times to the right.
Uh-huh.
So this is 3 times greater than that one, or the other way around, whichever way. But they're different. There's a difference by 3. Right, -2, -5.
All right.
So we're gonna guess that x is small. Okay.
Okay.
Okay. So what do I ignore here?
The minus x.
Minus x.
Yeah. But I got confused. Oh, do you know the top two?
Yeah. Plus x.
Oh, okay.
Makes sense. I can get rid of both of those.
Yes, that's where I got confused at. Okay. Okay, so we shouldn't distribute the x first.
No.
Okay.
Leave it until you make your assumption and then do your math.
Got it.
Okay, and then it became super easy, right? Because now it's just
Yeah.
9.099 divided by 0.099 again. So it's just x equals 6.1 times 10 to the -5.
Yes.
So you have to
Wait,
leave
let
one of
me-
the x's.
Say it again.
You have to leave one of the x's there to solve for something.
That one because it's not being added or subtracted to anything.
Okay.
Right. Only remove x's that are being added or subtracted to something.
Gotcha. Okay.
Because basically what we're saying is that x is so small that once you add it or subtract it to some number, it's still just a number.
But then multiplying it would change it a lot if it's small.
Exactly.
Okay.
Okay. So our Ka is our x value. They're equivalent.
Yep.
Okay.
Okay. Hello, everyone. Future links in here. When we were doing the problem in SI, what I forgot to do was check to make sure that our x is small assumption is right. So we'll do that real fast right here. So we take our 6.1 times 10 to the -5 divided by our 0.099, which was our initial amount of the H2C2O4 minus. So that's the initial amount of that times 100. And so when you do that, you get 0.0616%, and that is definitely less than 5%. So we are good. Back to the magic. All that work, still not done, because we need pH, right? So now what we do is we take this number, right? Calculate this number now.
Why does it matter that we do that one first?
Huh?
Is that what the question? Sorry. Why does it matter? Like if we solve for that one first rather than the reactant side.
Oh, because now I'm trying to get pH, right? So the only reason I'm asking about that one is because it's H3O plus, right?
Okay.
Right. I'm just looking. We're looking for pH now.
Okay.
Right. So now we're just going to take the negative log of this. Let's do it over here. I'm all over the place on this board. So pH is in the negative log of 0.099 plus 6.1 times 10 to the negative fifth. So what is
I got one.
Yeah.
I also got one.
I got one.
Okay, so the first size table, you need that X value to plug into the initial concentration of the second ice table.
Yes.
Okay, and then from there, you'll either do the X is too small approximation or the quadratic formula. You'll get that X and plug it in for the at equilibrium for the products. Right.
For the products.
Okay, and then, or would it be for, it'd be for the base? Because like in the one we just did, you plugged it in for the, like you didn't even worry about the conjugate base. You plugged it in for the conjugate acid. Hope I'm using those words right. I think I am.
Yeah, this is the conjugate acid, you're right.
Yes. Okay, perfect. So you plugged it in for the conjugate acid.
Because I'm looking for pH, right?
Right. Oh, okay.
So I just need the H3O plus concentration.
So if it had been, okay, if it had been base, then you would have used your conjugate base.
If it had been a base, right? Yeah. If it had been a base, then here would have been, then I would have grabbed I would have looked at the equilibrium amount for HOH minus, right, to get POH. And then from POH, I would go to pH.
Okay.
Right. Yeah, the only reason I chose this is because I want my pH, and to get pH, I need the H3O plus concentration at equilibrium.
Got it. So you could have used the C2O4, but you would have had to do like a extra step.
Well, this
C2,
well, I can't get pH from this amount, right?
Okay.
I need my pH equation, right? Is pH equals negative log
The concentration.
H3O plus.
Right. Got it. Okay.
Right. So that's this part right here. This is my.
Yes. Okay. Got it. Okay.
Questions?
I think I'm good.
Okay.
I'm good too.
Awesome. Well, that's basically. I think he did a problem kind of like this one. The initial amount might have been different, but this is basically what the video covered. It's kind of sort of. I would still watch him just in case I either said something wrong or said something different than how he wants it. So you know.
Yeah, I'm still gonna watch him. I was just
hadn't done it yet.
This helped a lot.
Yeah, no worries. No worries. We're all. It's a crazy times learning right now.
Mm-hmm. Yep.
Okay, perfect. Thank you.
No problem.
Yeah, thanks.
Thanks for coming, everyone.